is really the 600 multiplied by 1200 actually. Okay, so it's going to be 72 and 1, 2, 3, 4, 4 zeros actually. Okay, square feet. Okay, square feet. So this is really the area that you can get, the maximum area that you can get out of the available 2,400 fencing actually. Okay, so this is just one way to solve it actually. Another way to, for example, deal with it, if you don't want to do the second derivative test, I prefer second derivative test. You know, it's not necessary that second derivative test always work, because it can also give you, so if you're not getting any decision out of second order derivative test, then you have to kind of check through the first order derivative test as well actually, because there can be some points where the second derivative test, where the second order derivative is equal to 0 actually, then the test would be inconclusive. Okay, then the first order derivative test would be the more beneficial to use actually. Even, I mean, if you think a bit carefully about it, then you can even say, for example, if I say you to solve this through the closed interval method actually, try to solve this problem through the closed interval method actually, then how can I solve it actually? So for solving this problem through the closed interval method, the first thing would be to find the interval actually, that on which this function makes sense and this must be defined. Now, what is the one of the basic thing that, you know, an area must satisfy? An area must be non-negative. It can't be negative actually. You can't have a negative area. So if I, for example, assume that, okay, you know, what is the x for which the a of x is greater than or equal to 0, we can find it. And how we can find it? We can find it, for example, 2400x minus say 2x squared, say greater than or equal to 0. And you can say that, okay, so if I divide by, for example, 2, you're going to get 1200 minus, say, x times x greater than or equal to 0 actually. Okay, so you want these two quantities to be what do you call greater than or equal to 0. Now, under what conditions these two quantities can be greater? So that they can be greater under, you know, two possibilities, that either both are negative or both positive. Okay, both negative or both positive. Now, can these both quantity be negative? I don't know about this quantity, but I know about this quantity that this can't be negative. Why? Because this is representing the length actually. This is representing the length. So if it is representing, what do you call, the length, then this means that this quantity can't be negative. So saying that, okay, their product is negative, okay, their product, the both quantities are negative does not make sense. So you have to exclude that case actually, because at least one of the quantities can't be negative. So the both of them should be positive. So x should be greater than or equal to 0, and say 1200 minus x should be greater than or equal to 0. That is, x must be less than or equal to 1200 and must be greater than or equal to 0. So this is really the interval, okay, from where if you choose your x, okay, your area is going to be maximum. No, your area is going to be non-negative. So the interval from where you can choose your x is 0 to 1200. And now once you know, for example, this result, okay, then the key thing would be to find, what do you call, once you know this, then through the closed interval method, if you want to make a conclusion, okay, through the closed interval method, if you want to make a conclusion, then you need to compute your area at 3 points. So first you need to compute at 0, you need to compute at 1200, and you need to compute it at, what do you call, the critical point, which is 600 actually. So if you compute your value at these 3 points, and out of these 3 points, whatever gives you a maximum value would be the, what do you call, the point that would be the point at which the area would be maximum actually. So what would be A of 0, for example? A of 0 for sure is going to be 0. If you substitute, say, 1200 in the area, you're going to get, what do you call, A of 0 is 0, A of 1200 is also going to be 0 if you compute it. Yes, 1200 times 2 is going to be there. And A of if you compute the A at the 600, so it's going to be 72000. So this is the area. So this is the X, this is the length for which the area of the fencing, okay, this rectangular region is maximum. Okay. So again, from the closed interval method, we also got a conclusion that the area would be maximum if the length of these two walls are 600 actually feet. Okay, and obviously, and this would be 1200. So I hope this made a little bit of sense to you actually. Okay, so let's move on to another interesting problem. So the interesting problem is this. Imagine you have a 1-liter liquid, okay, with you. So you have some kind of liquid, okay, and you want to create a can, okay, to put that liquid in actually, okay. Now, if you want to create a can that can hold that 1-liter liquid, okay, then what, so if you are a manufacturer, for example, of some cold drink or maybe some paint or maybe something that is liquid, okay, so I want to sell liquids and I want to create a container for it actually. The question is, what should be the ideal size of the container to contain the 1-liter of the liquid actually? Why finding this ideal size is important? The container should not be too big or it should not be too small actually. Okay, it should not be too small. So if you want to, it should be of the reasonable size actually that can hold 1-liter of the liquid. And why manufacturers will be interested in finding a reasonable size which can carry 1-liter of the liquid? Because they want to reduce the cost of creating the can actually, okay, because for the creation of can you need material and you need the manufacturer need to buy several things, okay, and so we want the minimum of those materials actually, okay. So our can shouldn't be too big or too less. So what should be the appropriate size of the material, or what should be the appropriate dimensions of the cone actually that we, of the container that we need, cylindrical container that we need to put, for example, a 1-liter of the liquid actually. Okay, so this is what is our next problem actually. So what we want to do, this is next example. So what we would like to do, so we have a 1-liter of liquid and we want to put it in a container actually. Okay, So what should be the ideal size of the cylinder, okay, so that it can contain the 1 liter of the liquid, and the cost of creating that cylinder should be also minimum actually. And the cost of creating that cylinder would be minimum if we use what you call the ideal material actually, okay, the reasonable amount of material to create that cone. Okay. So if you're gonna create a big container, you're gonna need more of what you call material to create it. Okay. And if you're gonna say, you know, for example, make a small container, probably it will not carry the 1 liter of the liquid actually. Okay. So we want an ideal size actually. So what we would like to do, so we want to find the dimensions. Okay. We want to find the dimensions of cylinder. Okay. That will minimize the cost. That will minimize cost. Okay. That's what is really the step one. We identified what is given, what is known, we understood the problem, and now we want to move ahead. So what should be the next, you know, simple topic? The next step is really to make a picture actually. So how does a cylinder look like? So the cylinder looks like this actually, which has really 3 parts. One part is top lid, okay, this top lid. The other part is this bottom lid, okay, and the third part is this body of the cylinder actually, okay, the body of the cylinder. Now let's call, okay, so let me put for example, so if it is a cylinder, this cylinder must have a fixed radius actually, and basically we are interested in that radius. So first a quantity that we are interested in, that what should be the radius of the cylinder? That is going to be the radius of top lid, radius of the bottom, and the radius of entire cylinder actually. And what should be the height of the cylinder actually? Okay. What should be the radius of the cylinder and what should be the height of the cylinder, so that surface area can be minimized. The surface area, okay? The surface area of cylinder, let's call it A, can be minimized. Okay? Now, how to compute the surface area of what do you call the cylinder actually? Okay, so I mean, if you see the cylinder from the top, okay, if you see the cylinder from the top, so let's assume that this chart is like a cylinder actually. So if you see the top is a disc actually. The bottom is also a disc. Okay, so it has 2 parts. So one is, you know, the top, which is a kind of a circle of the radius r, okay, circle of the radius r, and the bottom is also a circle, or the disc of the radius r. It's not a hollow circle actually, so it's a filled kind of a, what do you call, so it's a disc actually, okay, it's a disc with say radius, with radius r, okay, with radius r actually. So this is the top and the lid and bottom. Now, how much should be the, what do you call, so what should be the area of this actually? The surface area of the cylinder is going to be the surface area of the top, surface area of the bottom, okay, and the surface area of the body. So what should be the surface area of what do you call the lid actually? Okay, this disc actually. So it should be, the area should be what do you call pi and r square actually. Okay, so should be pi r square for top and pi r square for bottom, so it should be the 2 pi r square. Okay, so this is the surface area of top and bottom. What should be the surface area of the body? Now I say, for example, just imagine in your head actually that, for example, I give you this cylinder and I say to slice it actually. So assume that it doesn't have a top and doesn't have a, what do you call, a bottom, and I say you to slice it. It's to cut it and open it actually. Okay, so I can for example take a page out of a paper and really show you this. Let's take a page out of a paper. Okay, not a reasonable paper, but okay, let's assume that this is a cylinder. Okay, this is a cylinder, top, bottom, and I cut this cylinder. Okay, so what I'm gonna get actually? So I mean, if you see, if it does not involve, for example, this rough kind of path, okay, then this cylinder is really going to be, the body of the cylinder is going to be a rectangle actually. It is just going to be a rectangle. Okay, it's going to be a rectangle. So what should be the area of this rectangle? Can we figure out the area of this rectangle, which kind of represents, which kind of, you took the rectangle and you folded it and made a cylinder out of it. So what should be the dimensions of the rectangle actually, if you open it? The dimensions of this rectangle should be what? So this must be really the height of the rectangle. Okay? And what should be this? So if you, for example, make a cylinder out of this rectangle, okay, if you make a cylinder out of, say, for example, this rectangle, so what you're going to get? You're going to get a circle. And whatever is the circumference of the circle is really the dimension of the rectangle actually. Okay? So rectangle. So this is a cylinder, for example. Okay? So it has two dimensions. One dimension is really this height, okay, and other dimension is this circumference. So when you open it, so this is height and this is really, what do you call, the width of the rectangle actually. And what is the width of this rectangle? The width is equal to the circumference of the circle actually, circumference of the disc. So what is the circumference of the circle with the radius r? So it is, for example, 2 pi r. Okay? 2 pi r. So this area, the body, the surface area of the body is going to be 2 pi r and h. Okay? 2 pi r and h. Where I must say r is the area and h is the height of the cylinder. So what should be the total surface area? The total surface area should be, what do you call, 2 pi r square plus 2 pi r h. Okay? 2 pi r h actually. So, can you see this? Pi is a number, r is what do you call, radius of the disc or the cylinder, and h is the height of the cylinder actually. Now, again the area depends on the two quantities. One is radius and other is height actually. So if you want to, for example, make it more kind of a interesting problem, okay, you want to apply the techniques of single variable optimization, then you have to kind of get rid of what you call at least one of the variable actually. And how you can get rid of one of the variable? Okay, the way to get rid of one of the variable, so the volume of the cylinder is pi r square. So pi r square is the volume area of the bottom multiplied by the dimension h actually. So this is going to be the volume. Okay, and we want that this volume should contain what you call the 1 liter of what do you call the liquid actually. So let's call it, say, so 1 liter is 1000 cubic centimeter actually. So 1 liter is 1000 cubic centimeters. So you can use this relationship actually. So 1 liter is 1000 cubic. 1000 cubic centimeter actually. So I can say that the volume is equal to the 1000 cubic centimeter. And once you have this, now you have a way to get rid of one of the variables. For example, if I get rid of, say, h, then h is going to be 1000 divided by pi r square. By the way, it is not necessary that you should use, say, 1000 cubic centimeter as the unit to represent 1 liter. Okay, I mean you can use any other units as well, I mean, if you like actually. But in order to contain 1 liter of say liquid, you need this much space, 1000 cubic centimeter at least. Okay, this is the standard unit. So height is what you call 1000 over pi r square actually. So if I substitute this into this equation, then my a is going to be a function that is purely a function of r, and this function is going to be 2 pi r square plus 2 pi r times 1000 over pi r square. This is what it is going to be. So just get rid of, say, r and r, and you got a function of r, which is 2 pi r square plus 2000 pi divided by, so pi and pi will be cancelled as well actually. Yes, pi and pi will be cancelled as well, so it's going to be 2000 by r. So this is what is really the required surface area actually, okay, to contain the 1 liter of to contain the 1 liter of the liquid. Okay, and what we would like to do, we want to minimize this surface area. So if, for example, if you are, you want to make this cylinder out of tin or some material actually, you don't want to overuse the material because it's going to cost money to you. Okay, so I want to minimize this area. So how can I minimize it actually? So we can do the same thing again, that okay, now do the step 4 of optimization actually, find the critical points. Okay, critical points. In order to find the critical points, you need to differentiate it, and if you differentiate it, you're going to get 4 pi r plus the derivative of the 2000 by r is going to be minus 2000 divided by 1 over r. So it's like r power minus 1 actually. So the derivative of r power minus 1 is minus r power minus 2. So in other words, minus r square. This is what is really the derivative of it. And then, equate it to 0 and solve this equation. So if you solve this equation, what you're going to get? So for example, the first thing is multiply this equation by r square, or solve it the way you like actually. So it's going to be 4 pi r cube minus 2000 equal to 0. Okay, this is what that you're going to get. So this means r cube would be 2000 divided by 4 pi r cube, and 4 is going to be what? So it's going to be 500 actually, 500 divided by pi. So the r is going to be the cube root of 500 divided by pi, I can treat it as 3.14. Okay, approximately. This is what is going to be really approximation. So approximately, this is what is going to be the result. Okay. So what we should do? Then what we can do is that, okay, either you can, for example, so that's a critical point actually. So that's a point, okay, where the A prime approximately becomes 0. Okay. A prime becomes approximately 0. So what we should do next, so I can, compute a second order derivative of it, for example, and make a substitution and see what you get actually. So if you, or you can use first order derivative. Let's compute, for example, the second order derivative. So if you compute the second order derivative of it, of the first order derivative, so it's going to be 4 pi, okay, minus 200, and now we have r power negative 2. Okay, r power negative 2. So if you have r power negative 2, so it's going to be 2 r power negative 3. Okay. So this is going to be then plus 4,000 divided by, what do you call, r cube. Okay. And now if you see, so if I, for example, substitute this, the value of r here, this value of r here, so 4 is a positive number, pi is a positive number, 4,000 is a positive number. This is a positive number actually, because r cube is what? 500 over pi actually. So if you substitute here, this number altogether is going to be a positive number. So on substitution, for example, the value of r is cube of 500 divided by 3.14, or maybe what do you call pi. So the number that I am getting on the other side is a positive number. I'm not interested in what that number would be. Okay, so I can, make a calculation, but I don't need to calculate it. I just want to know that what is the sign of the second order derivative at this point. So it's a positive number. Why? Because r is a positive number, 4 pi is a positive number, 4,000 is a positive number, so the sum would be a positive number. So this is a positive number. So if it is a positive number, that means that this r is minimum. This is a minimum actually. Okay? So in other words, if you choose this radius, you should have a minimum, what do you call, surface area. So what we can do now, next, take this r, substitute it here, okay, and get the value of h. And once you calculated this h, substitute it back into, for example, A, so that will provide you the minimum area, okay, of the minimum surface area of the cone actually. So you know the radius, substitute it here, you're going to get height, substitute the r and h in this formula and you're going to get this minimum, what do you call, area actually.